Greetings, Dr. Dan with Optimal Optics, here to introduce Unit 16, Pupils, Ports, and Stops. So I have a bunch of definitions here. These are words that you should be familiar with since you are now in Unit 16 an expert in optics, and people will expect you to understand what these terms mean. So a field stop is an opening that limits the extent of the field of view. An aperture stop is an opening that limits the brightness. Generally, it's the smallest opening, but not always. The entrance pupil is the image of the aperture stop seen from object space. And the exit pupil is the image of the aperture stop seen from image space. The entrance port is the image of the field stop seen from object space. The exit port is the image of the field stop seen from image space. And another definition of the chief ray, it's the ray that passes through the center of the aperture stop. Now we're going to construct a camera, an old-style camera with film in the back. Nowadays cameras have light-sensitive electronic elements in the back of the camera. So they accomplish electronically what the film used to do chemically. So the opening is the shutter. Again, in the old-style cameras, you could adjust the size of the shutter. Now it's done automatically. There's a convex lens in the camera, film in the back. The focal point of the lens is about there. And the opening, the shutter, that's the aperture stop. That limits the amount of light that enters the camera. From object space, there's nothing in front of the aperture stop. There's no lens in front of it, so the opening is also the entrance pupil. However, if you look at the aperture stop, the shutter from the right side, from image space, it is within the focal length of the convex lens, and it produces a virtual magnified image, and that's the exit pupil. Now, if we place an object, let's say arbitrarily here, and send a ray along the edge of the aperture stop and the edge of the lens, you'll see that that ray hits the top of the camera and never gets to the film. What that means is that the film itself is actually the field stop. That back of the camera where the film extends from the top to the bottom, that is the field stop. From image space, from the right side, it looks the same. There's no lens there, so it's also the exit port. Now, if we place the secondary focal point where the film is, the entrance port is at infinity because the object for the lens is at infinity. So now that we've learned about entrance pupils and exit pupils, we can learn a new magnification formula for optical systems. Magnification equals the entrance pupil diameter divided by the exit pupil diameter. How quaint. Now recall from Unit 14, when we learned about binoculars, the objective is the lens in the front. And it also happens to be the aperture stop, and because there's no lens in front of it from object space, it is also the entrance pupil. The exit pupil you can observe by looking through the eyepieces, looking at the eyepieces, and by rearranging the formula above, we can calculate the exit pupil diameter as the entrance pupil diameter divided by the magnification. So if you have binoculars with 6x30 on the label, you can easily calculate the diameter of the exit pupil by dividing 30 by 6, and you get 5 millimeters. Now, if you have a manual camera, you'll see it has what are called f-stops or f-numbers on it. And they're listed as 2, 2.8, 4, 5.6, 8, 11, and 16. What is an f-stop? An f-stop is the focal length of the lens of the camera divided by the diameter of the aperture stop, which is the shutter in front of the lens. Now recall from basic geometry that the area of a circle equals pi r squared. So that means if you double the radius or double the diameter, you're going to get 4 times the area of the circle. And if you have H-A-L-V-E, the radius, or halve the diameter, you're going to produce a circle with 1/4 or 1/4 the area. The area of the aperture obviously influences the amount of light that enters the camera. The bigger the aperture, the more light that gets in. So the f-stop or the f numbers are calculated so that each consecutive number produces an aperture size where the radius is about half, or the diameter is about half the radius of the previous f-stop or f number. And therefore, for each consecutive f-stop, 1/4 as much light enters the camera. Now, not only does the aperture size influence the amount of light that comes into the camera, it also influences what's called the depth of field. The depth of field is how much of the picture is in focus in front of and behind the target that you're imaging. So here's a visual representation of that. We have a very small aperture. We're taking a picture of this arrow target, and the lens is behind the aperture. And with a large depth of field, a lot of the stuff in front of the target and behind the target will be in focus when you take your picture. And the opposite happens when you have a very large aperture. Taking a photo of this arrow target, maybe a couple inches in front and a couple inches behind the target will be in focus, and everything else will be blurry. That's a small depth of field. I went to Walgreens the other day to get my pictures developed, and there in the photo department I saw Cinderella, her arms crossed, tapping her foot. And I asked her, "What are you doing here?" And she said, "Someday my prince will come." So here are my binoculars. You can see they're labeled 7 by 35. The 35 means that the diameter of the objective lens, the big lens in front, is 35 millimeters. And the 7 means that the magnification of the binoculars is 7x. The eyepieces on the other side, you see their diameter is smaller than the diameter of the objective lens. So you might think that the eyepieces are the aperture stops, but that's incorrect for binoculars. In fact, the objective lens captures all of the light and funnels all of that light back through the eyepieces. So the objective lens is the aperture stop. Those white circles that you see are the images of the objective lens focused through the eyepieces. So you're looking at the aperture stop from image space, therefore those are the exit pupils. And their diameter is 35 divided by 7 equals 5 millimeters. This is important if you want to use your binoculars at night. Your eye pupil can dilate up to 8 millimeters in the nighttime, and you're not getting as much of the dim light into your eye if you're looking through these binoculars with exit pupils of 5 millimeter diameters. You want to try to get binoculars with as large an exit pupil as you can if you use them at night.